Hi, welcome to this module. In this module we will learn photolithography. In last module what we have seen? We have seen photoresist, positive photoresist, negative photoresist, bright film mask, dark film mask, how each mask and photoresist are related and what will happen if I use a particular photoresist with a particular mask. So, in this one let us see how the process flow for photolithography, what are the process for of the photolithography. So, for the first step, if you see, you have to see the slide and please concentrate. The first step is to take a substrate, all right. First step is to take a substrate. The next step is, if you have the substrate, it is assumed that this, if it is silicon and you want to deposit a metal, the substrate is oxidized silicon wafer. If you are using glass, no need of oxidizing the glass, because glass itself is an insulator. So, let us say we are using glass here, glass. Next step is to spin coat photoresist, spin coat photoresist. Spin coating photoresist, what kind of photoresist we can use? We can use positive or negative photoresist. In this case we are using a positive photoresist. So, what we have done? We have spin coated the photoresist on the substrate. Next step is to perform soft bake. This bake is similar to baking. Soft bake means you will load this wafer on a hot plate. The temperature of the hot plate is 90 degree centigrade and the time that will load the wafer on the hot plate will be 1 minute. This is called soft baking. This much is easy. Next step, after this we have to load the mask. Right. So, which kind of mask? So, I will take a wafer. I have my wafer with a photoresist, and on that I will load a mask. Let us say this mask is a bright field mask, right, cross section. Bright field mask, all right. Positive photoresist, glass, bright field mask. Next step is you expose. So, first you have to load the mask, all right. Then you have to align the mask. I will show you the loading aligning process in some other modules. Right now, you just understand you have loaded the mask and then you have to expose the wafer. Exposing wafer is with what? You know, exposing wafer is with UV light, right. UV, what is UV? Ultraviolet light, all right. Next step in this is you have to unload the mask, right, unload the mask, and after unloading the mask. So, this step itself has loading of mask, load mask and exposure, load mask and exposure. After this particular step we will go for unloading the mask. After unloading the mask, the next step would be photoresist developer. You have to develop the photoresist, right. So, we will dip this wafer in photoresist developer. We will dip this wafer in a photoresist developer. Okay. So, now what kind of photoresist we have used? Positive photoresist. What is the mask that we have used? Bright field mask. So, the unexposed region will be stronger. unexposed region would be stronger. So, when I develop my wafer right in a positive photoresist, then what will I have? In a positive photoresist developer with a mask which is bright field, then I will have my photoresist protected in the area which was not exposed with a UV light, which was not exposed with a UV light. So, let me draw it like this is easier. This is my photoresist, this is my glass. You get it what I am saying? The area which is not exposed will get stronger. So, you have a area which is not exposed stronger in this case, right. Now, what is the next step? The next step is a hard bake. Next step is a hard bake. In hard bake, we will use hot plate at 120 degree centigrade for 1 minute. We will load the wafer on the hot plate and temperature would be 120 degree centigrade for 1 minute. Right. Next step is you have to inspect the wafer in microscope, inspect the wafer using microscope. All right. So, what we have to do, let us repeat this one once again, right, and then we will take an example of a heater. So, you understand that how we are using the photolithography process. First you take a substrate, next step is you spin coat the photoresist. It can be positive photoresist, can be negative photoresist, right. Now, let us say in case of the third step is soft bake. Soft bake is done at 90 degree centigrade 1 minute on hot plate. Fourth step is you load the mask, right, and expose the wafer with UV light. Fifth step is photoresist developer, and sixth step is you inspect the wafer using the microscope, right. Now, let us quickly see, instead of positive photoresist, if I have used a negative photoresist, what will happen here? What will happen? I will have this pattern. I will have this pattern. The area which is not exposed becomes weaker. The area which is not exposed becomes weaker, right. So, now if I want to have this pattern, I will use negative photoresist. If I want to have the same pattern which is here in the mask, then I will use a positive photoresist. If I use positive photoresist, what will I have? We have just seen in positive photoresist, we have pattern like this, is not it? Easy, extremely easy, right, extremely easy. Okay. So, let us take an example of a heater. So, you understand the whole process. We say micro heater, micro heater because the width and the spacing between two lines are of micron dimensions. So, micro heater. So, first step in micro heater is you have to take a substrate. Again we will use a glass to make it easier, we take a glass as a substrate. Next step is not photoresist spin coating, but we have to deposit a metal. What is the metal? We are using micro heater. So, let us use nichrome, right. Next step after this, what is the next step? The next step is I have this nichrome, on the nichrome I will spin coat positive photoresist, I will spin coat positive photoresist, all right. Next step is here soft bake, right, soft bake soft bake is done at 1 minute, soft bake is done for how much time? 1 minute, temperature is 90 degree centigrade, and it is we are using hot plate, we are using a hot plate, right. The next one is we have to, next step is we take this wafer, we have our material which is my nichrome, on that you have positive photoresist, on this positive photoresist we will load a bright field mask. Bright field mask has a pattern which is here, I am showing it, bright field mask. I am sorry for the notification from the phone. Okay, this is your bright field mask, right. I have my bright field mask. Then next step is I will perform UV exposure, right. After this, too big. After this, if I go here, I will dip this, unload the mask and dip the wafer in a photoresist developer. When I dip this wafer in photoresist developer, what will happen? This is my positive photoresist, this is nichrome, this is glass. What will happen? The area which is not exposed becomes stronger and the area which is exposed will become weaker, right. After this, what is the next step? Next step is hard bake. Hard bake is done at 120 degree centigrade for 1 minute on hot plate, right. Next step is we will dip this wafer in nichrome etchant, this is wet etch, When I dip this wafer in nichrome etchant, what will happen? I will have nichrome only in the area which was protected by the photoresist. The remaining nichrome will get etched in the nichrome etchant. Wherever my photoresist was there, that photoresist would act as a mask and it will protect the nichrome below it. The remaining area, the photoresist will get etched. Easy. After this, I am going all the way here, okay. Stay with me. After this, I will dip this wafer, in acetone. What is the role of acetone? It will strip off my photoresist, this is my photoresist, this is nichrome, and what is my substrate? Substrate is glass, right. So, when I dip this wafer in acetone, right, what will I have? I will have let me just redraw it. my heater ready, my heater would be ready. Let us see once again. Okay. First step is my substrate. Second step is you deposit nichrome. You deposit nichrome using electron beam evaporation, or sputtering. Third step is I will spin coat positive photoresist. Next step is I will perform soft bake. Soft bake is done at 1 minute 90 degree centigrade hot plate. Next step is I will load the mask. Which kind of mask? Bright field mask. Next step next step is after this 4 number, 5th number is your bright field mask. The next step is UV lithography, which is 6, right, UV exposure. After UV exposure I will dip this wafer in photoresist developer, so that will be my 7th step. After photoresist developer I will perform a hard bake, 8th step. After performing hard bake I will dip this wafer in nichrome etchant, which is my 9th step, right, and then finally I will dip this wafer in acetone, which is my 10th step, right. So, once again glass, then nichrome, then positive photoresist spin coating, soft bake at 90 degree centigrade for 1 minute on hot plate. Next step is to load the mask. This is a bright field mask. After that you will expose this wafer with UV lithography with UV light. So, you have UV. Next step would be to develop the photoresist. So, we will dip this wafer in photoresist developer. Then we have a hard bake. Hard bake is done at 120 degree centigrade for 1 minute on hot plate, followed by a nichrome etchant, because we had to etch the metal where we do not require it, we have to pattern this metal, right, and the metal will get etched where it is not protected by the photoresist. After that you dip this wafer in acetone. When you dip this wafer in acetone, acetone will act as a stripper for nichrome material, and you will have a heater which is made up of nichrome. You understand? So, this is a process for fabricating a micro heater. What you have learned? You learn a photolithography steps to fabricate a micro heater. So, if you want to understand further about micro machining, right, you machine everything, and then machining is like if you have a substrate and you remove a part of the substrate. If you remove the part of the substrate, it is called machining. So, if you see the slide of fabrication methods, another very important step is bulk micro machining, and bulk micro machining is where you take out the bulk of the material. For example, if I have the silicon substrate, let us say oxidized silicon substrate, and I want to create a diaphragm in this oxidized silicon substrate, then I have to create a window from the bottom, right, window from the bottom. That means I have to etch the silicon dioxide from the area where I want to etch the silicon wafer. Now, what I will do is I will etch this wafer so as to create a diaphragm, right. I will etch this wafer so as to create a diaphragm. So, this is, let us say if it is 4-inch silicon wafer, then this the thickness will be about 500 micrometers, and if I am etching 400 micrometers to create a 100 micrometer diaphragm, if I am etching 400 micrometer, then the bulk of this material is etched. So, I have machined it at a micron scale, right, such that I have removed only 400 microns, but out of 500 microns. So, a bulk part of it is removed, is etched or is machined, and that is why it is called bulk micro machining. You see, bulk micro machining, right. So, this is an example of a bulk micro machining, and it is the oldest micro machining technology. Then techniques involves selective removal of substrate to produce mechanical components. So, if I have, let us say this selective removal of material, that means what? If I have silicon dioxide, my silicon which is protected by silicon dioxide will not get etched. only silicon that was not protected by silicon dioxide, when we created a window in the previous design, will get H, which is like here. Now, here if I have a strain gauge on this silicon wafer, right, these are contact pads, this and these are contact pads, and then this is a strain gauge. So, if I apply a force, on this strain gauge, right, if I apply a force, then what will happen? This diaphragm will bend. This bending of diaphragm will cause the strain in the strain gauge. If it is a piezoresistive material, I will be able to see the change in resistance. So, the this is a bulk micromachining technique. It is also used to create or produce mechanical components. It is accomplished by physical or chemical process, right, with chemical being used more for MEMS production, right. So, we to etch this silicon wafer, we will use potassium hydroxide, TMAH. These are both chemicals. So, chemical being used mostly when we are going to fabricate MEMS based sensors. The chemical wet etching is popular because of high etch rate and selectivity. Isotropic wet etching, where etch rate not dependent on crystallographic orientation of substrate and etching moves at equal rates in all the directions, while there is anisotropic etching, where etch rate is dependent on crystallographic orientation of the substrate. So, when you talk about bulk micromachining, then there is chemical way, there is a dry etching, there is a wet etching. In dry etching and wet etching, you have isotropic etching and anisotropic etching, and where the anisotropic etching would be depending on it depends on the crystallographic orientation, while in the case of isotropic wet etching, it is not dependent on crystallographic orientation, and etching moves at equal rates in all the directions. The another one is called surface micromachining. So, let us take an example. I have a silicon wafer, all right, like this. This is my oxidized silicon wafer. On silicon wafer on which I have grown oxide, so it becomes oxidized silicon wafer, all right. And then what I am depositing is, I am depositing a material which is zinc oxide, and I am patterning it using photolithography, right. That means, I am depositing zinc oxide, then next step is photoresist spin coating. Next step is, so this is, let us say this one is my photoresist, spin coating photoresist. Next step is soft bake 90° 1 minute hot plate. Next step is, I will put a mask, I load a mask is bright field mask like this. After loading a bright field mask, this is my bright field mask. Okay. After loading bright field mask, the next step is UV expose. After UV exposure, next step is photoresist developer. When I develop my photoresist, then what will I have? I will have my oxidized silicon wafer, right, and then I will have my zinc oxide material. On that I will have my photoresist like this. When I develop this wafer after UV exposure, right, in photoresist developer I will have this wafer. Then if I dip this wafer in zinc oxide etchant, what will happen? I will save my zinc oxide only where the photoresist is there. Only where the photoresist is there, zinc oxide will be saved. Remaining area zinc oxide will get etched. Remaining area zinc oxide will get etched. Next step is I will dip this wafer in acetone. If I dip this wafer in acetone, the PR will get stripped off, PR will be stripped off. So, if PR gets stripped off, I will have this wafer where I have silicon dioxide, silicon dioxide, and the top layer is zinc oxide. All right. Now, on this zinc oxide, if I deposit a metal, and if I dip this zinc oxide in zinc oxide etchant, after depositing metal, if I dip this zinc oxide this silicon wafer, this oxidized silicon wafer with metal into zinc oxide etchant, what will happen? You understand? See, there is a oxidized silicon wafer, we have patterned zinc oxide in this particular step, right. This is a step for zinc oxide. Now, on this I am depositing a metal using physical vapor deposition, and I am dipping this wafer in zinc oxide etchant. So, what will happen is the zinc oxide will get etched. Zinc oxide etchant will not affect the metal, which is let us say gold. Zinc oxide etchant is 1% HCl, 1% HCl will etch zinc oxide, it will not etch gold. So, this way I am able to see a cantilever, I am able to fabricate a cantilever, and everything that we have seen here is a machining, but the machining is done at the surface level. I have not etched any bulk part of the material, bulk part of the substrate, right. So, everything is done at the surface level, and that is why the machining that we have done at surface to create this cantilever of a metal which is my gold, then this is called a surface micro machining technique. And the zinc oxide layer that we etched to create this cantilever, that zinc oxide is called a sacrificing layer or sacrificial layer, the layer that we are sacrificing to create the cantilever. So, it is called a sacrificial layer. All right. This is an example of your surface micro machining, all right. So, what we are looking at here, we see that the process starts with a deposition of thin film that acts as a temporary mechanical layer called sacrificial layer, right. Then the next step is the device layer are constructed on the top. For example, in our case it was metal, depositing and patterning of structural layer, removal of temporary layer to allow movement of structural layers, we create a cantilever, it can vibrate. Then what are the benefits? The benefits of this particular technique is variety of structures are possible, sacrificial and etchant combinations are there, uses single side wafer processing. See, if I want to create a sacrificial layer, everything is done on the top of this, no, everything was done on the top. But if I want to create a diaphragm on the back side, that means that I am creating a structure here and I am also etching from the back side. In this case I require a wafer which is double side polished. In this case I can use a wafer which is single side polished, right, single side polished versus double side polished wafer. So, if it is single side polished, the cost of fabrication will be less compared to a double side polished wafer. Then the further advantage of surface micro machining is that it allows higher integration density and lower resultant per die cost compared to bulk micro machining, that is the advantage. And the disadvantage or limitation is that the mechanical properties of most thin films are usually unknown and reproducibility of the mechanical properties is kind of difficult, right. So, that is another point that we need to understand, that the mechanical properties of most thin films are usually unknown and reproducibility of the mechanical properties is important. So, if you see, this is an example of the bulk micro machining and surface micro machining. You can see in bulk micro machining there is a isotropic etching and then there is a anisotropic etching, right. There is a isotropic etching and then there is a anisotropic etching. Then we have surface micro machining. in surface micromachining you can see here surface micromachining, right. In surface micromachining the first step is that you have a substrate, then you have sacrificial layer, that you pattern it, then you deposit a structural layer, finally you sacrifice the sacrificial layer, right, in this particular form. So, you have the cantilever. The same thing is shown here, right. You pattern the photoresist, right, and then you have the sacrificial layer which is patterned like this. On that you deposit the material or the structural layer, right, and then you again pattern it with photoresist, right. You sacrifice the sacrificial layer and then you have your complete micro machined profile, right. See sacrificial material on the substrate, there is a pattern photoresist and you deposit this. So, you will have this. Next step is a material layer, next step is the patterning of photoresist, followed by a sacrificial layer etching, followed by the pattern that you want to see, right. Easy bulk micromachining, surface micromachining, right. Let us go to the next step. So, before we go to the next step, let us stop here, because I do not want to create a module which are very big. It is kind of boring, no, to sit and listen for a long time. We are not used to that, except that there is a movie. If there is a movie, we stick to the bed, we stick to the sofa, and we can watch for 3 hours continuously. But if it is a lecture, after a certain point we need a break. So, let us take a break. And I will see you in the next module, where we will discuss about the bonding techniques, we will discuss about the benefits and trade offs of bonding technique, what are MEMS, where exactly the MEMS are used, and many more applications, followed by understanding how to design several sensors, what are the process flow for designing each sensors, and then we will see how we move ahead. I want all of you to understand how the lab component looks like when we talk about the sensor fabrication. We will see how we can create a microfluidic platform. We will see lot of equipment within the laboratory, and we will talk about that at some later point. But right now you understand that, okay, micro machining, there is bulk micro machining, there is surface micro machining. In the fabrication methods, there are the bulk micro machining is the oldest fabrication technique or micro machining technique. Then we learn about lithography. In lithography, how can we pattern it, what are the steps for lithography. More or less, if once you understand photolithography, you can fabricate almost all the kind of sensors. So, its the process remains same, right. What is the process? Let us quickly understand the process. First is your spin coating of photoresist, next is a soft bake at 90° 1 minute hot plate, next is you load the mask, next process is you expose with UV, next process is you unload the mask and dip the wafer in a photoresist developer, followed by hard bake, which is done at 120° centigrade for 1 minute on hot plate, and then finally a inspection. If there is a metal, then followed by metal etching, and then finally you have to remove the or strip the photoresist. The stripping of photoresist is done by dipping the wafer into acetone. So, this is the process that if you remember, you can fabricate most of the sensors, right. So, that is the gist of this particular module. I will see you in the next class, where we will talk about bonding and further MEMS techniques, and where are they actually being used in the commercial products that we use on a daily basis. Alright, so till then you take care. I will see you in the next class.